So slope, y sub 2 minus y sub 1 over x sub 2 minus x sub 1 is equal to m. Or if you have y equals mx plus b, obviously just look at m. There, it's pretty easy to see what the average rate of change is if you got a line. But what if you don't have a line? How do you determine average rate of change? Well, we're going to put a couple points down. I'm going to put a point at -3, -5. I'm going to put a point at 6, 1. And I'm just going to draw a generic function that connects the two. Okay, so here we go. Some type of function connects the two together. Now, the average rate of change tells us kind of about the direction that the function is heading. Would you agree that the direction of the function in general is heading up? However, is it heading up the entire time? No, here it's heading up, and then it's actually heading down, and then there's actually times where it's flat at kind of 0, and then it heads up again. So the way that we determine the average rate of change is we determine it by the segment that connects the beginning point and the end point. And we determine the slope of that segment. The way we determine the slope of that segment is we look at y sub 2, which is 1, minus y sub 1, which is -5, divided by x sub 2, which is 6, minus x sub 1, which is -3. And you can see you get 6 over 9, or 2/3. So that means on average, that line is heading up 2/3 of a unit for each unit it goes over. Sometimes it's greater than 2/3, sometimes it's less than 2/3, but on average it's 2/3. So the way that we express that, and it's the same formula as slope, we just use different notation. What we do is we call this endpoint, or this first point, we call it A, and the last point we call it B. So the output of A, we say, is f of A. And the output of B, we say, is f of B. So for other functions, we like to use this notation. F of B minus f of A, all divided by B minus A. And that's what we refer to as the average rate of change of a function. So we're going to look at it graphically, and we're also going to look at problems algebraically. You have f of x equal to 4x minus 3. Everybody should be able to look at that and determine what kind of function it is. What shape does this make? It's a line. What's the slope? 4. So therefore, the average rate of change should also be 4. Let's show that that's the case. I first do f of 4 minus f of -2 divided by 4 minus -2. So I plug in 4. What do you get when we plug in 4? 13. Plug in -2. Good. -8 minus 3 is -11. All over 4 minus -2. Or 24 over 6, which is 4. And we said that the average rate of change should come out to be 4. Agreed? Okay. You find the average rate of change for the next function. Go. Over the interval -2 to 1. I got 4. Does it always come out to be 4? No, it's just by chance. Okay? Any questions on those examples? All right. Identify the intervals on which the functions are increasing or decreasing. You should be able to look at a graph and identify when it's increasing. Super easy. Increasing or decreasing. So from -5 to what? -2. Union with, when else is it increasing? 4 to 5. Decreasing from -2 to 2. We would say in that section, it's neither increasing nor decreasing. The slope is 0. Yes, question. You use parentheses because at this point, it's neither going up nor going down. Neither is happening. Same way here. At this spot, it's neither going up nor going down. The slope is flat. Yes. I'm trying to think of how to phrase that and what we're talking about, but I would say no. We simply just leave it off of the list. Okay? We would say that's neither increasing nor decreasing. Increasing if it's on its way up, decreasing is when it's on its way down. Neither one is happening at those locations. So we remove it, we don't use brackets. So in this situation, it's increasing from negative infinity because we have an arrow all the way over to 1, 2, 3, over to negative 3. And then it's increasing again from 1 to 4. It's decreasing in between negative 3 to 1. So again, we do not put brackets because neither is happening at those spots. Take out your graphing calculator. What I really want you to be able to do is I set up, you're like, okay, that was super easy. I set that up for you so you can then do these two problems. What you want to be able to do is be able to look at your calculator and determine when functions are increasing and when they're decreasing. I go to y equals, and I type in x cubed minus 9x. And I zoom standard, zoom 6. What you're going to do is you're going to sketch a picture of that graph. Now, I don't actually get the whole graph in my window, so I'm going to adjust my window so I can see more of it. I'm going to take the y values and drop them down to negative 20, and the other y values increase them to positive 20. I'll have a tick mark every 5 units. So I've changed my window and adjusted it, so now I have a more attractive graph. Okay? So if you use your trace button, you can see that, at this point, it looks like the graph is dropping. It's decreasing. And if you look over here, it looks like it's increasing. So it looks like at this spot right there is when that change happens. And as you look at the x coordinates, those estimated, but I'd like to come up with a more exact number. Does anybody remember how we could use our calculator to come up with that exact value up there? Very good. Second, calculate maximum, number 4. So I move to the left, press enter. I move to the right, press enter. And I press enter on guess, and it has it at negative 1.73. So therefore, I am increasing from negative infinity to negative 1.73. How would I come up with that lower spot? Yep, minimum. Second, calculate number 3. We go to minimum. We drop down to that lowest spot. As we move to the left, press enter. As we move to the right, we press enter. We press enter on guess. And sure enough, we're located at 1.73. So it's increasing from negative infinity to negative 1.73, and then from 1.73 to infinity. It's decreasing in between from negative 1.73 to 1.73. In case you didn't know, 1.73 is approximately the square root of 3, which is actually the actual value in this situation, but someday we'll show you how to find that exactly. Any questions how I did that? Then we look at our last example, and then you can have time to work. You should be able to get at least half of your assignment done in class. Y equals negative 2, and when you go for cube root, you have some options here. So negative 2 times a cube root, you can go to math, and in math, you can select your cube root function. Or what I do is I just go parentheses, x minus 3, and I raise it to the 1/3 power. Very good, Nicole. Must have just had a birthday. You're really smart. And I'm going to zoom standard, zoom 6, and I get this graph. Somebody earlier said it was an ugly graph. I guess, beauty is in the eye of the beholder. I think it's pretty cute myself. So. Can you say that again, Alex? Decreasing the whole way. Alex says something here that's really important. As you look, as I move left to right, it looks like my tracer dot is moving down the whole time, doesn't it? And so it looks like it's decreasing, 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 and he's 95% correct. But there's one small issue. You see, we really classify a slope into one of four categories. We just say it's positive, negative, zero, or undefined. And notice in this situation, we want to categorize positive and negative. We want to rule out zero. We want to rule out undefined. Is there any spot here where the slope is undefined? For just a very, very, very short moment, for 1 point, at just 1 point, the graph is headed perfectly straight up and down. Anybody want to guess what x value that happens at? It is exactly 3. There's no mistake that there's an x minus 3 in the equation. It does happen at 3. So we say decreasing from negative infinity to 3, union with 3 to infinity. So we leave 3 off from the list. It's increasing, never. I know it seems strange to suggest because it looks like it's obviously just decreasing, but anytime you get that vertical straight up and down, we have to say it is undefined. It's neither positive nor is it negative, no matter what the graph is transitioning in the process. And that's it.